All right, this is going to be the beginning of a new unit, conveniently titled Introduction of Logarithms. And in this unit, you're going to be taught some stuff you've never seen before. It's going to be a little bit challenging because you don't really have anything to base this information off of. But we know that. We know that like as it's being taught to you, and this is going to take a few weeks to get through. All right, to set the stage for all of this, I'm going to ask this question and see if you can remember what the answer was that goes with it. What does it mean for a function to be one-to-one? All right, so question, what does it mean for a function to be one-to-one? Did you answer the inverse relation to a function is a function? I don't know if you would put it in those words. There's a lot of other ways that you could mention this thing. You might have used horizontal line test and stuff like that. But the best definition of it is the one that I wrote down here, which is to be one-to-one. That means that the inverse relation to a function is a function itself. There are some functions whose inverse relationship, how all things are undone, does not produce what is a function. All right, now that may require you to do a little bit of work on what does it mean to be a function. To be a function means that for every input, you only get one output. Okay, we want to make sure that when you take the inverse and you flip everything backwards, that those inputs will also only have one output. Anyhow, there's a lot going on there, and feel free to look up some of that old stuff in the notes or go do a Google search on what is one-to-one, and hopefully the thing that comes up is not simply just going to be the horizontal line test. Though it is very useful, and I do that when I'm trying to answer questions, but it is not the end-all to it. In our previous unit, we talked about exponentials, right? We did all the graphing, and we did application problems of it and stuff like that. Okay, what I want you to do is I want you to graph that, okay, and then we're going to talk about whether or not it's one-to-one. Hint, it is going to be one-to-one, right? Then based off of that, we're going to start to see what happens with logarithms, or what a logarithm actually is. Okay, so pause video now. Go ahead and complete this table and see if you can plot all the dots that go along with it. Here is the table completed, and I went ahead and already plotted the points and graphed that, so you wouldn't have to watch me do that portion of it. This exponential function you might recognize as being one of the most basic graphs that we've used, and I'm not going to go through the whole table. That should be stuff that you're already familiar with, and if you need, just go back and look at the old notes on that stuff. All right, so here's a picture of it. And the question that's posed at the beginning is it one-to-one? Is the inverse of this itself going to be a function? Okay, now let's talk about what it is to be a function. To be a function, it has to pass the vertical line test. So if I were to take a vertical line and just run it along this whole graph, I'm looking to see if the graph happens to touch that line twice. In other words, we're asking, look, does this graph ever like curve over itself? Does it backtrack at any point? And if it doesn't, then it's called a function. And what that really means is that for every input, you get exactly one output that goes with it. Okay, but if we were to try and reverse all this stuff, to do everything backwards, would that be a function as well? Well, we have a test for that one, which is called the horizontal line test. Okay, so at the bottom, you've got this asymptote, and that does pass the horizontal line test. It's just very, very slowly moving up. Okay, and then definitely you can tell through here that it's going to pass the horizontal line test. Again, only contacting once is the rule. Okay, so this function is going to be one-to-one. That means that its inverse is going to be a function as well. So the big question is actually going to be this. What is the inverse of this function? We know other stuff. We know like x to the second power, its inverse is going to be the square root of x with a limited domain, of course. Cube functions are going to be cube roots, right? For every function that we have studied so far, we have been able to address an inverse, and for the most part, those inverses, you could probably just pick out what they are. But what the heck is the inverse to having a variable and an exponent place? Okay, so where we're going to begin with this is just to draw the picture of it. It must exist. The function's 1 to 1. Its inverse has got to exist. There's got to be one. And our question is just what it is. So how are we going to do that? We're going to go back to some of the very basics, which is the inverse is the switching of the domain and the range. It's the switching of those two. So if I just plot all of these coordinates backwards, I'll actually start to create a picture that would be the inverse of this function. Okay, so go ahead and do that. Just plot all these as y values. I'll give you one as an example. So let's say I'm looking at that coordinate. And instead of plotting 1, 2, I'm going to plot 2, 1. Go over 2 and then up 1. All right, go ahead and plot all those. You should be able to connect it to look like a curve. And that's going to be our inverse. All right, here's our inverse. You got that graph by plotting all these points backwards, right? You go out, well, we couldn't do that one because it's off chart, but you go out 4 and up 2. So you go out 4 and up 2. You can go out 1/2 and then down 1. Right, go out 1/2 and then down 1, you get a point. There's your graph. All right, you might, now that you see the picture, if you didn't think of this beforehand, you might recall that that a function and its inverse are always going to be reflections across the line y equals x. So that line here. All right, little reflections of those things there. By the way, hint for a little bit later, you do have a horizontal asymptote for the exponential function. That means that when it flips over, you get a vertical asymptote for the inverse function. Okay, so here's what we've done. You couldn't see this part earlier, but it said graph the inverse using the coordinates. So we flipped all the x's and the y's and we got this picture to go along with it. All right, this function, number one, it has to exist because an exponential function is 1 to 1, so it has to exist. But now we got to think about what is that graph? And we haven't seen it before. It looks familiar as some other things with the vertical asymptote. It looks like a rational function, but it isn't one. Okay, it's got its like own shape. There's nothing over here, right? The green graph is only on that side and there's nothing on that side to it. So it is a new function here. It is called a logarithm, and the way that you write it for this particular one, so f-1 is referring to the inverse of our other function, which was the 2 to the x, is going to be called this. Apologize for that line there. There's a 2 as a subscript. All right, and you read this as log base 2 of x. That's what this will be. The really weird thing here is that the logarithm is a made-up function, right? We had exponential functions, and I think we can all contemplate why they work. I mean, we talked about bank accounts and all this stuff, and exponential growth and decay and all that business. But those functions were 1 to 1, so there had to be some function that was its inverse, but we couldn't grasp, well, which function is it that we already know exists that would be that one? So what we did is we just made up a new function and we called it a logarithm. Okay, here's the formal definition of a logarithm. For positive numbers y and b not equal to 1, by the way, those are just mentioned as, they have to be true, but we usually don't worry too much about them at the beginning stages of like trying to learn how this stuff works. So don't pay too much attention there. Okay, but for all that stuff, the logarithm of y with base b written this way is defined as follows. Okay, now underneath it, I go over like how it's read, log base b of y, so I'm gonna read it that way. Okay, log base b of y equals x if and only if b to the x power is equal to y. Okay, so let's look at this piece first. This is a basic exponential function. You have some base, maybe 2, raised to the x power, and it gives you these y values. The inverse is going to involve in some way the x's and the y's switching roles. The domain becomes range, range becomes domain. Okay, but it appears in this format. Right? You can't just switch the two and then call it its inverse. That really doesn't work out. But we can write it this way. We can say, let's keep the same base, but it's written here as a subscript to a logarithm. And then we switch that x and the y value. So now the y is inside the function and the x is outside. Okay, and a really neat thing about this is because our function is designed this way, because we made it up this way, we're actually able to jump back and forth between logarithms and exponentials. That's one of the fundamental things that we end up doing with logarithms and exponentials together, is just bouncing back and forth between them. And we're going to cover all that in the examples that I have underneath here, and that'll be pretty much the main focus of today's notes. Okay, so I do this as like more of a visual thing. If I had a logarithm and I wanted to change into an exponential, what I do is I just cover up the logarithm. I pretend it's not there. I cover up the logarithm and then I switch that x and y value, like switching your domain and range. So if I move the x over into this position, but to the y to the other side, it looks like that, except that b isn't a subscript anymore. It's just a normal type base. Now, if you needed to go from exponential to logarithm, you just switch those two and then kind of put a log in front, adjust the leveling of everything, and that's what you'll get. All right, let's see this actually work. All right, first, let's see what we got. We're going to write these in their other form. So if I have this exponential expression, so there's no x's and y's in here because that would just be confusing. But I give you an exponential expression that you should accept as being true, that 2 to the 4th power is 16. I'm getting out a calculator right now. Okay, let's just make sure everybody's on the same page here. Okay, 2 to the 4th power is equal to 16. That is a true fact. That one's going to be true as well. 4 to the 0 power, anything to the 0 power is 1. Okay, so then the claim is you can change this into a logarithm. Good, you can see it up here. All right, we can change it into a logarithm that will also be a true expression. Okay, and what I will do is introduce the log, write that down. Whatever the base is to the exponential, I should say, that is going to be the base to the logarithm as well. So that's a subscript of a 2. But then the 4 and the 16 are going to sort of exchange places. They're going to move to different sides. So I'm going to have a 16 is equal to 2. No, sorry, 4. Okay, and you would read this as log base 2 of 16 is equal to 4. So there's a special function that's called log base 2. There's a different logarithm for every base that's out there. This is log base 2. And if you put a 16 into that function, you get back 4. Now on my calculator, my old 84 calculator here, to pull that feature up, I go to math, then it's going to be choice A. So I just type in alpha math and brings it A. So then you get to type in your base, which is the 2, and then I put in 16. And the claim is this is going to come back and say that the answer is 4. And it does. All right. Over here, anything to the 0 power is equal to 1. Okay, but I'm going to change this to the logarithm version of all these numbers interacting together. This is going to be log base 4. Your base is still your base, but as a subscript. The output becomes the input, and the exponent becomes the output right there. Okay, so you know that that one's going to be true. Let's type this other one in. And it's going to be base 4. We are inputting a 1, and we get back a 0. Okay, so right now, all we're doing is just kind of getting used to the fact that there's something called a logarithm that is the inverse of an exponential, and we get this neat property that we can switch between the two of them. Okay, so if I got a logarithm, taking that to exponential, these I actually think are easier because I can actually like cover stuff up. I can cover that logarithm up, and I can say that 12, that's this 12 here, raised to the 1st power is equal to 12. And of course that makes sense. We don't need to type that one in. All right, over here, cover up logarithm. I'm going to have 1/4 raised to the -1 power is equal to 4. So keep the base and then move those two around, and you should see that that makes sense. You raise 1/4 to a negative number. That negative is actually going to flip it, and -1, that's all it does. It flips it over and it gives you back 4. All right, example 2, we're going to go a bit further with this. We're going to evaluate logarithms based off of the fact that we can change these into exponentials. Now, this is something that you can do for very particular problems. You can't do it for every problem that works out there, because these are very dependent on what types of numbers we use. If we're using numbers that are raised to powers, it has to be things that are like that. Okay, here's the trick. Do I want to type it in first? I'll go ahead and type it in first. Okay. Okay, we want to evaluate this thing here. We want to know what it's worth. Okay, and you always have the option to do it in a calculator, and almost every cell phone will allow you to do this in some way or another, that you could do this. Okay, but let's do it by hand first. All right, what I'm going to do is, there's an answer that I want this to be. I'm just going to call it x. I'm just choosing any letter there. This is going to equal some value that I'm going to refer to as x. So I'm going to put that in there as a filler. I think this is really important if you're going to do it by hand, that you actually write this out. Okay, and then I'm going to change into an exponential. I'm going to cover up the logarithm. I've got a base 4. That is now going to move into the exponent position. That's why it's important that I write it down. That's going to move into the exponent position. The 64 is going to move to the other side. And then based off of this, I should be able to answer the question on my own. What power do I raise 4 to get 64? And that is 3. 4 times 4 times 4. And there it is. All right, let's try it again. Set this equal to x. We're going to get 5 to the x power, so the base to that is going to be equal to 0.2. Pause for a second here to see if you know what is important about 0.2. It's a fraction, and expressed as a fraction, it is 1/5. Oh, so what exponent do we raise 5 to get 1/5? And that would be a -1. Let's box these. I'll let you type that one in on your own later to verify my work. All right, last, set this equal to x, so I have something there. If you don't do that, you might just get stuck and have absolutely no idea what to do with it. But once you see that, then it clears it all up. All right, I've got 1/5 raised to the x power has got to equal 125. Okay, so 125 is actually 5 cubed. So you were responsible for knowing your cubes up to 7. You should at least know what 7 cubed is. Okay, so 5 cubed is 125, but it's upside down. So x is actually going to be a -3. You want to flip it using that negative to turn it into a 5, and then you want to cube it to get up to 125. All right, at the end here, I have a couple of things that I need to share with you. For the most part, they're just definitions, but they're going to be very, very important as you move forward throughout the unit, and they're going to keep popping up as we go along. I don't have any examples to go with these. This is just information for you right now. We have 2 very important logarithms. One is called the common logarithm, and that one's going to be a base 10, okay, log base 10. Now, you can have any base that you need for a logarithm. At the very beginning in the notes, I did log base 2. But there's these 2 that are really important. One of them is called the common logarithm, and that's when you have base 10. I mean, kind of think of our number system, and it might make sense when we call it the common logarithm. Okay, but if we are doing log base 10, it will normally be printed as log x. Like it doesn't actually show the base. We just remove it from there. So if you do see this where there's log and then no base written, that just means that it's log base 10. Okay, and on your calculators, yeah, my calculator is a little bit hard to see some of the buttons, but look, there's a button that just says log, and if I press that one, okay, so here's some of the older stuff I typed in. If I just press the button that says log, it just shows up like that. But it means that it's actually log base 10. So if it's helpful to rewrite things with the 10 so you can move it around and whatever, makes sense to me. But be aware. All right, the other is called the natural logarithm, and that's going to be using base e, which we saw e to be very important in the last unit. So if you have log base e, right, instead of writing it that way, you can actually write it with an ln. That is an L and an N. It's not a capital I and then an N. This is going to be log natural. All right, you know, in most other languages, adjectives come after the nouns. Okay, so we have a logarithm that is natural. So instead of calling it NL, we just call it ln. But you need to know that. Okay, so very, very rarely will you ever see this printed, log base e of x. You're going to see that a lot, the natural log of x. I personally do believe it is helpful when you're working on a problem to change it into log base e, because then it fits the script of everything else that you're doing, especially when you're new at the content. So feel free that if you ever come across natural log of x or log x, just to change them so that you can see the bases.